Have you ever wondered how scientists can actually see a molecule? I mean, atom by atom, when it's millions of times too small for any microscope? Well, today we're going to dive into the brilliant technique that makes it all possible: nuclear magnetic resonance spectroscopy.
It's a huge challenge in science, right? You can't just zoom in on a molecule. You need a super clever, indirect way to build the picture. And that's the exact problem that nuclear magnetic resonance, or NMR, was invented to solve. It's basically a way of asking atoms, hey, where are you, and who are you next to?
So, here's our roadmap. We're going to start with the big problem of seeing the unseen, then get into the really cool physics of something called the electron shield. We'll see how that creates two different states for an atom, how we can actually read the signals they send out, and finally, how all of this shapes the world around us in some pretty amazing ways. Okay, let's start at the beginning. Molecules are the building blocks of literally everything, but they're just impossibly small. So if you want to understand how a new drug works or figure out what a new material is made of, you have to know its structure. And for that, you need a special tool that can sense things on an atomic scale.
So here's the secret sauce. Certain atomic nuclei, like the ones in hydrogen atoms, for example, have this property called spin, and you can pretty much just picture them as microscopic spinning magnets. Now, what do magnets do? Just like a compass needle, these tiny little guys will all line up when you stick them in a powerful magnetic field. And that's the very first step in any NMR experiment.
Now, this is where it gets really, really cool. See, a nucleus isn't just floating out there by itself. It's surrounded by a cloud of its electrons, and you can think of this cloud as its own personal force field, a shield that's constantly protecting it.
And this effect has a name, of course: electron shielding. Those electrons buzzing around the nucleus, they generate their own tiny magnetic field. And that field actually pushes back, just a little, against the big, powerful magnet we're using. So what's the result? The nucleus doesn't feel the full blast of the external field. It's being, well, shielded.
So it's pretty simple. The denser that electron cloud is, the stronger the shield, and the more protected that nucleus is. It's kind of like wearing thicker sunglasses on a bright day. Less of the energy from the outside actually gets through to you. This one idea is the key to, well, everything in NMR.
So this whole idea of protection leads to two different states for a nucleus. You see, depending on its chemical environment, like what other atoms it's bonded to, a nucleus can either be really well protected, which we call shielded, or its protection can be stripped away, and we call that deshielded.
Let's just break this down. On the left, you've got your shielded nucleus. It has a nice, thick electron cloud, so it feels a weaker magnetic field. But a deshielded nucleus, maybe it's next to an atom that's really electron-hungry, like an oxygen atom, that's pulling that electron cloud away, leaving it exposed. Now, to tell these apart, we hit them with radio waves, and each nucleus resonates. It's like it sings at a very specific frequency, like a tuning fork. The shielded one, feeling a weaker field, needs a higher frequency to get it to sing. The deshielded one, feeling a stronger field, sings at a lower frequency. And that difference, that's how we can tell them apart.
Okay, so we've got these two different states, shielded and deshielded, and they're each singing at a different frequency. But how in the world do you turn that chorus of signals into a map that you can actually read?
Well, think of it like this. Since every nucleus in a molecule has a slightly different neighborhood, each one sends back its own unique signal. A nucleus with a strong shield sends one kind of signal, and one with a weak shield sends another. You put all those signals together, and what you get is a completely unique molecular fingerprint.
So how do chemists read that fingerprint? They look at a chart called a spectrum. On one side of the chart, you've got what are called upfield signals. These come from those well-protected, shielded nuclei. On the other side, you've got downfield signals from the exposed, deshielded ones. And by simply mapping out which signal is which, they can piece together the molecule's entire structure, almost like a jigsaw puzzle. It's incredible.
So all of this might sound like some pretty deep, abstract physics, right? But why does understanding this tiny atomic effect really matter? Well, it's because the applications are absolutely enormous, and they impact all of our lives, whether we know it or not.
I mean, just look at this list. The most famous application is probably magnetic resonance imaging, MRI scans. But it's also absolutely critical for discovering new drugs, for making sure our food is safe, for developing new materials, and even just for chemists in a lab making sure they've actually made the right thing.
Just let that sink in for a second. The exact same physics that lets a scientist map out a single molecule is what allows a doctor to see the tissues and organs inside your body. An MRI machine is really just a giant NMR machine. and it's tuning into the signals from all the hydrogen atoms in the water that makes up most of our bodies.
And look at that number. Over 60 million times a year, this fundamental principle of electron shielding is used to diagnose diseases and save lives. That is just a staggering testament to how understanding this invisible world can have a very, very real impact on all of us.
So here's the real takeaway. It all starts with a simple concept, an electron acting like a tiny shield for its nucleus, and it blossoms into one of the most powerful tools in all of modern science. It lets us decode the structure of our world from the atom up.
And that leaves us with a pretty fascinating question to ponder. We've already figured out how to map molecules and look inside the human body without ever making a cut. So what's the next great invisible frontier that a clever bit of physics will let us explore? Thanks so much for joining this explainer.